All right. Okay, so we started our study of quantum chemistry, excuse me, on Monday. And we left it at a point where we found out that one of the things that was proposed at the beginning of the 20th century was that light had the property of sometimes behaving as a wave and sometimes behaving as a particle. And the photoelectric effect explained by Einstein was the one that essentially put the nail in the coffin of light being just purely electromagnetic radiation. So many of the properties of electrons, for example, in the Bohr atom, we talked about how Niels Bohr proposed that the hydrogen atom had electrons essentially orbiting the nucleus in specific discrete orbits with quantized or discrete levels of energy, but that you could transition from one level to another by pumping in energy, let's say electricity, and then the electrons would fall back to a more stable state, and in the process release that energy they had absorbed in the form of light. But the question was, why is the atom organized that way? So the proposal came. Let's go to our PowerPoint here, if I can find it. Oh, here we go. And the proposal was that much like light has dual nature, so does the electron. You got to understand, up till this point, it was believed and accepted that the atom was made of these three subatomic particles, neutrons, protons, that were clumped in the nucleus, and then electrons that were somewhere out there outside the nucleus. Now Bohr was proposing the electrons were essentially orbiting the nucleus. But the idea here was, what if electrons, in the same way as light, actually have properties both of particles and of light? And so, let me get to our markers here. Okay. So the question was, why would the energy of electrons be quantized? Why would they not exist over a whole spectrum of different energies? All right. So in 1924, Louis de Broglie reasoned that just like light, the electron is both particle and wave. Now, what kind of a wave is what's important here, all right? So I'm going to borrow here from the the structure of a guitar, all right? Now, when we talked about waves last time, we usually assume we're talking about something that is sourced at some point and then travels through space, like, for example, light coming from the sun to the earth, or let's say the waves in the ocean going from the horizon all the way to the shore. But in a guitar, what happens is that you have a string that can vibrate, and the vibration of that string translates into the vibration of the air molecules around it, which then gets transmitted as a sound wave, right? So let's look at a guitar very quickly, how a guitar is made. Oh, sorry. Gotta make sure these things work here. Okay, so this is the body of a guitar, and those of you who are familiar with guitars, some of you actually play guitar. I used to play guitar. I haven't played like in 6 years or so, and my guitar actually is kind of buried deep into a storage unit that we had to open last year when we were going to sell our house, and I have not retrieved it yet. But anyway, of course, the idea is that, as you can see here, the body of the guitar is essentially a box, and then there's a long arm here that has where the strings are attached, and there's a fretboard, and essentially you press down, and therefore you shorten the distance over which the string vibrates, right? So that's the way it works. So if we look at it, there's several ways that you can change the notes, right, on the guitar. So one of them is the 6 strings on the guitar have different thicknesses. You can see here from right to left. You go from the 1st to the 6th string. You can see how they're progressively thicker. They're also sometimes made of different materials, so they have different densities, which means they vibrate at different frequencies. So let's see how that works. If we look at here at a, let me take you to this little website here. And let's play with. So, you know what? Let me make sure that this is going to work here. Hold on a second. Computer sound. Okay, got it. All right. So, for example, here what I'm going to show you is what happens when you plug the string going from the first through the sixth string. In other words, from thinner to thicker. All right. So here comes first string. Second string. Third string. Fourth string. Fifth. And sixth string. So obviously what you can tell is that as you go through a progressively thicker string, you get a lower pitch of the note. And that's basically because what the string is doing, it's vibrating between, the bridge, the two ends of it. And the faster the vibration, in other words, the higher the frequency, the higher the pitch. But because the thicker strings are thicker, they don't vibrate as fast, and therefore they generate a lower pitch sound. Now, another way of doing this, again, is to shorten the distance over which the string vibrates. So when I press down on these frets, essentially I'm forcing the string to vibrate between, the bridge there and just the, place where my fingers are pressing down. That means that now the string travels a shorter distance and therefore can vibrate more times in the same amount of time. In other words, higher frequency, which, like we said, translates into a higher pitched sound, right? So if we go back to this, again, we're going back to this web page here. And let me find a different one that I had in here. If I can find it, here we go. So what I'm going to do here, again, remember we heard the first string here, right? So this is the first string here. Now let's see what happens if I hold the fret on the fifth fret. And here's on the 12th. So you can see how, again, let me do that again. I think I just picked the wrong one here. Just a string, fifth fret, 12th fret. So you can see that as I shorten the distance over which the vibration happens, I get a higher pitch sound. That's because you have a higher frequency. So this phenomenon is what is called standing waves. Notice that the wave that the string forms is actually not projecting out into, endless space. It's actually being held between the two limits here, right? So essentially, the idea here was that that is kind of like the type of wave that an electron has. So here's a representation of these waves. So pretend, I don't know if you can see the whole animation here, but this is as if, let's say, pretend you have a wave coming from the left to the right. It bounces at the right end and it bounces back towards the left. And as they overlap each other, they generate this oscillation here that you see going up and down, right? Let me isolate just that one combined wave. You can see it here. So notice that what's happening is that this string is essentially oscillating, but it's oscillating between two limits, right? And what happens is that between those two limits, if you adjust what is the distance between them, that tells you essentially what type of wave you can fit in there and what wavelengths you can fit. So let me show this picture over here. This shows you essentially, let's say, two boundaries between which a string is vibrating, all right? Let's say the distance between the two boundaries is L. Notice that in the top one, we essentially have a wave that acts as if it is essentially going half of the wave to one end, and then perfectly bouncing back and reconnecting on the left side. Now, if we had no loss of energy, like if this were not a string, if this were like a perfect wave, it would continue on forever. Notice that this wave essentially has a wavelength that is equivalent to 2 times the distance between these things, right? Notice that the second one, the second example here, has a full wave going from left to right. So it starts there at the center point and then it ends up there and then bounces back and essentially can generate itself back and forth, and you generate this stationary wave. The first one is what we call the fundamental. In music, this would be harmonics. And so actually, the vibration of a string in a guitar is actually more complex than what I showed you. Actually, during our break, I'll play you a video so you can see all the little more details of the physics of it, in case you're interested. So notice that there are only certain specific wavelengths that you can fit in here, such that when the wave goes from one side to the other, it can bounce perfectly back and reconnect at the origin and then bounce back and forth. So there are certain wavelengths that are allowed and other wavelengths that might not be allowed. So for example, it looks like although a wavelength that is 2/3 of the length of the string is allowed, a wavelength that is 1/3 of that distance might not be allowed. So you know what I'm saying? All right, so let's look at some other features. Notice that there are some points along here where the actual amplitude of the wave is 0. We call those nodes. So a node is a position or a place on the standing or stationary wave where there is 0 amplitude. Also, we could rearrange these equations here. So right now I have it for every value of n, right? You can have what is the wavelength that would fit inside that particular harmonic. But you could also rearrange these equations in terms of what L is. Notice that in this case, we could say that L was essentially the distance of half a wavelength. And if I count in half wavelengths, the second harmonic, L, would be 2 times a half wavelength. The third harmonic would be 3 times a half wavelength. In other words, for every harmonic, in other words, every where I'm trying to fit, n number of waves, the length that will fit them is essentially n times a half that wavelength. So there is a direct relation between the wavelength that you can fit and the distance over which that wave can travel. That means that there's going to be several wavelengths that are not allowed. They're going to be discarded. They're going to essentially create a wave that self-destructs, all right? So here's what Louis de Broil said. He said that the electron, like light, is both particle and a wave. Now, we just talked about an oscillating string. But in the case of the electron, remember, the idea was that the electron is orbiting around the nucleus. The Broil was saying the way it orbits is not as a particle, but as a standing or stationary wave, except that instead of being linear over a linear axis, it's actually running over a circular axis. Notice that, let's say, for example, in this case, let's say that I start my orbit right at this point. Let's call this 3 o'clock, and I'm going to go around the orbit until I arrive at the other end. Notice that this wavelength is such that when the orbit is completed, you end up exactly where you started. And so the wave can keep on propagating itself. On the other hand, in this case, notice where I started here, the wavelength was such that when the electron finished its orbit, it did not end up at the same spot that it started. Therefore, this wave would not last one orbit. It would not be allowed, all right? Now, in the previous example, we showed you a relationship between the wavelength and the distance between the limits. But this is a circular one, so it has a different form of the equation. We would say essentially that in a circumference, which has a dimensions 2 pi r, where r is the radius, you would only be able to fit certain types of waves, which will be n times the wavelength. Or alternatively, we could convert that into the other equation, which has lambda would be equal to 2 pi r over n. A very similar equation to the one we just studied earlier, except that this is for a circular motion. So based on this and other calculations, de Broglie came up with what we call the Broil equation, which is this one here. This is an equation that gives us the wavelength that would be associated with the orbit of an electron around the nucleus, all right? And let me tell you what these things are. Here, u would be the velocity of the electron, all right? And of course, m would be the mass. And don't forget this h here is actually, remember, this is Planck's constant. That's the Planck's constant. So that is essentially how de Broglie made this proposal, all right? Now, I want us to spend a little time here, and I'm gonna, bug you here with some heavy-duty math, perhaps. Hope you don't mind, before we go to the next slide here. So let's go ahead and see how some of these derivations can be worked out.